All right, let's get started. So, like I said, this talk is going to be about managing your firewalls, essentially. And one of the problems I repeatedly run into is having firewalls that get completely out of date with rules that do not represent anything that is currently running in the infrastructure. And if you have a little bit of turnover in your company, one sysadmin did something one way 5 years ago, the new ones are doing it differently. Nobody wants to touch the old stuff because it might break something and you really don't want to. So that's a problem. And I'm going to talk about that problem and how we are solving it at my company, which is AWeber Communication, and I'm going to get into that. So who am I? I'm a systems and security engineer at AWeber. I'm mostly a Linux guy. I've been working primarily on Linux for the last 10 years. And I'm mostly a web infrastructure guy. Everything from web hosting to email hosting. And that's great because I work for a company that actually work on the web only. AWeber is an email marketing company, and we build a SaaS, software as a service application. We've been doing that for 13 years. And we have thousands of customers, I think something like 120,000 customers right now, monthly customers who use our web application every day. And so we have a pretty big web infrastructure. And we have a lot of moving pieces in there. And managing it is not always easy. So here's a problem, the main problem that we're facing at AWeber. So we have essentially monolithic firewalls at the entrance of our infrastructure, like pretty much everybody does. You have a big firewall that receives all of your web traffic, all of your internet traffic, and filters everything that goes out. The problem with those is they work very, very well at the edge, but inside your infrastructure, they don't work well at all. If you have two services that want to talk to each other, then you want to say server A needs to connect to server B, so I'm going to create a rule in my firewall that says server A is allowed to talk to server B. What that means is that for server A to connect to server B, everything needs to be routed through the firewall. That's the first thing. Second thing is that once your infrastructure gets a little bit big, you have thousands of rules very, very quickly that you have to manage. That doesn't scare at all. If you're the guy who has to figure out why a packet is not going through and all you get is a web interface with hundreds and hundreds and hundreds of rules in there, you're going to go crazy. You're going to hate that. The solution, I personally don't like routing everything through a handful of equipments. I've been, like I said, working with Linux for a while now, and I am really, really, really happy with the way the Linux firewall works. Netfilter. And this is a direction that we took at AWeber. That actually is a direction that they had taken before my time there. And we just continued that approach and improved it. We still have monolithic firewalls, but not everywhere. So we're going to get into that. A little bit of history first. The 70s firewall design. I said there were cats. Well, there's only one, but. All right, let's build a network. Hey, did you get a ping? Yeah, I got a ping. Everybody's happy. And we have 4 servers, well, actually 2 workstations, 2 massive servers, and we can ping each other. That's great. That's great. Let's move on. Let's add more servers to that. And nobody really thought of, hey, security. But thankfully, they did something really, really nice. That they built the protocol in a very simple way. TCPIP are not complex protocols. There's no fanciness happening. It's always logical. You can figure out what's happening. And that's one thing they did well. One thing they didn't do well is adding sort of security in the infrastructure. Nothing. No authentication, no access control, nothing. But we were fine in the 70s, 80s. Nobody was really using that stuff. I'm from France. In France, in the 80s, we had something called the Minitel, which was really just a terminal connected to your phone line. And you were connecting directly to the server of the French public ISP at the time, France Telecom, which was just a direct connection. There was no authentication. You could just listen to the signal and inject packets in it, and it was really easy. So that was happy times, and for hackers too, really happy times. In the 90s, this is really the most classic. Like when I was in college, this is probably the diagram I saw the most. You have your DMZ here and your production network and your office, and you put firewall and you make sure that no traffic can go from the DMZ to your office, but on the other way it works. And that's classic, and it works. It's actually better than what we had before. So you can actually put web servers in this part of the infrastructure, and they don't, if they get compromised, they don't compromise the entire network. That works well. You need, well, 3 firewalls, and very quickly people realize that 3 firewalls is great, but when one of them dies, then you lose everything. So you put 6, and you put VRP between them so they can do active-passive setups, and that kind of fixes it. And that works so well that the vendors started increasing their prices for firewalls, saying, hey, you need more, you need more, you need more, and you end up having to pay $150,000 for 4 firewalls. Like, wait, why? It's more expensive than the rest of the infrastructure, but whatever, it's needed. And that's the traditional approach. Then came the 2000s. And this is when things started to get a little bit hairy. For us, we're a web company, which means our production network is a DMZ. Everything goes in there. We actually don't care much about this or that. Well, actually, we do, because we have customer support. But most part, really the biggest part of the infrastructure, the money is here. So the approach of saying, hey, let's put something in the demilitarized zone, and that's going to be safe, doesn't work for us, because everything goes in there. And what happens is that you get hacked on one server. Well, that's great, but what's firewalling the inside of the DMZ? You can firewall the edge of the DMZ, but the inside of the DMZ, you can't really do that. So that started to be a problem for us. Another problem is, well, if we can't have multiple zones in there, we can start putting firewalls in there and route everything through it, like I was saying earlier, which is great, but it makes a route opening workflow really, really complex. I worked for a financial institution back in France, and they literally had a whole web application dedicated to requesting routes opening. You want application A to talk to application B? Great, here's your web form, and fit it up, and it's going to go through a workflow. It's going to take about approximately 4 weeks. And eventually a sysadmin is going to get in there and click the 3 buttons needed to open the port on the destination server. Eventually he'll do it right the first time. If he doesn't do it right the first time, then you have a second workflow, which is the diagnosis workflow that allows you to go through the web interface to diagnose the problem. Horrible, horrible. And no rule deletion workflow. That's the other really fun thing. 2005, firewalls don't work anymore. We need more. Yeah, the problem here is once everything is HTTP based, opening port 80 is not exactly useful because you just accept everything through port 80 and you don't look into the traffic. So vendors were like, that's not a problem. We can sell you new boxes that are going to solve that for you. I love it. So they came up with web application firewalls. Sure, why not parse your entire HTTP traffic into an appliance before serving it to the destination server and verify that it fits a canvas? So I have a formal security background, so I actually learned that stuff, and I loved it when I learned it. And then I started looking at the developer side of it, and I started wondering, why am I putting a security policy into an appliance when I could just tell the developers to do those checks in their application and remove the appliance that I have to maintain next to it? So this is when I realized that those kind of patches of the infrastructure are really, really expensive, really hard to manage, and keep up to date. They add latency to the network. They solve problems. They will solve problems if you have a legacy application in there, you have no way to touch that application, and you really want to have a way to block viruses, Trojan, anywhere, anything, to reach it, then yes, you need a web application firewall. If you're coding your own website, if you're coding your own application, you have control over the input validation or anything like that, really, you're better off putting it in the application, putting those checks in there, and not putting it into some sort of appliance. And then you get detection tools, NIDS, NIPS, HIDS, honeypots. Those are great, but they do not. The primary purpose of an infrastructure is to serve traffic, to actually serve production traffic for customers. If you start slowing things down with detection appliances, then, well, you kind of defeat the purpose of the infrastructure in the first place. So all of those additions to the infrastructure just made things worse and a lot more expensive, really a lot more expensive. We looked at upgrading some of our firewalls not too long ago, and the bill was around, I believe, $170,000 or $180,000 for a couple boxes. And at that point, we sat down and we were wondering, why are we not doing it ourselves with Linux? And we did it ourselves with Linux, in that for 4 servers that are serving the same amount of traffic and potentially doing gigabit traffic on each interface, that costed us $20,000. And the other advantage of that is that in the team at AWeber, nobody is really familiar with vendor technologies. And when we have to debug one of those firewalls, we always ended up Googling commands to figure out how to do a damn TCP dump on one of those firewall router or whatnot. If it's Linux, it's faster for us to manage. We understand it better. We work on that every day. It's just more convenient. The other thing that happened around 2005 is that developers literally stopped trying to connect application A to application B. They actually offloaded that to security teams and sysadmin teams. They stopped trying to do, hey, I have my web app here. I want to connect to this database because I can retrieve data. They started building teams saying, I'm on the developer side of things. You take care of opening the routes. I don't want to hear about it because it's a mess. And it's not exactly convenient. I don't know. I don't like that approach. 2010, congratulations, you're now routing your entire traffic through probably 3, 4, 5 boxes. I don't want to pick on any vendor particularly, so I won't give names, but I was at a user group not too long ago, and one of the famous load balancer WAF vendor out there was actually explaining how they can sit in between 2 data centers and inspect all of the traffic going from data center A to data center B. And it allows you to duplicate your data centers. You can even use the same IP ranges on both sides, and those appliances are going to understand that they are mirrors. So you can have the same IP on data center A, same IP on data center B, and your appliances at the top are going to take care of the routing. And I was sitting there, and really? Do you really want to do that? How do you audit your infrastructure? How do you end up like, you want to trace an action on your web application at some point. How do you know if this IP was on data center A or data center B? And once you end up routing everything through those few appliances, this is usually when you realize that you're hitting the 127 megabits per second limit that written in the fine prints of your contract that says it's your license limit, and you're supposed to buy a new license to get 128 megabits per second. Really? So that kind of approach makes vendors and their shareholders very, very happy. Your financial officer, not so much. Here's a different approach. A service-oriented architecture, and in this approach, part of the infrastructure are really isolated from each other. You don't build one infrastructure, you build services. Those services can be really, really small or really large, it doesn't matter. But from a logical point of view, they are independent services. So this is kind of the idea for web hosting infrastructure, where you have your caching service at the top, your front-end service, and then 3 other API services that will contain data. One of them could be accounting, the other one could be password management, the third one could be, I don't know, whatnot, statistics or whatever. And those services live independently. And your architecture is based on interactions between those services, dependencies. We know that service X needs service Y to function correctly. And service Z is accessed by front-end service and by service Y. Actually makes the architecture a lot easier to manage for everybody, including management, because they know what is needed to actually build, I don't know, a yearly financial report. They know that they need to connect to the accounting service and they need to connect to the customer support data, that kind of stuff. And having that represented at a logical point of view, really higher up, makes it easier to implement at the infrastructure level. I'm going to see that now. Another requirement, and that's really important for us because we're a web hosting company, so we really, really care about our uptime, is that we don't want any single point of failure. We want to optimize resource utilization, density, virtualization. We want to make sure that if we buy a server that's going to cost us 30 grand, we want that server to be using at least 50, 60, 70% of its CPU all the time and not just be sitting there waiting for traffic. This is another reason why I really don't like active-passive setups, because you end up buying 2 boxes that are 50 grand each, and the second one doesn't do anything for all year long. Doesn't do anything. So you just wasted $50,000 for nothing. When you have control over your infrastructure and you can do proper load balancing, you can use both boxes at the same time, double your capacity, and you're still redundant. And augment and reduce capacity rapidly, so that's usually cloud-related stuff. I'm not going to get into buzzwords, but the idea is some services are really, really, really small when they start. When developers come up with a new service, we're going to create a VM for them that really typically has 2 CPUs and 1 gig of memory. And that's it. That's all they're going to get. Eventually, if that service ends up being used by more services around it, we're going to grow that service. And we want to be able to do that. And every week we create new VMs for new services. We eventually destroy VMs for services that we thought were going to be used and are not used. And we grow disks as well. When you use virtualization, on Linux specifically, you can store everything on LVM volumes. You can take those volumes, grow them, multiply by their size by 3 or 4, and it's really easy. So that's really the key points that are really important for infrastructure. If you've played with Amazon Web Services, they have a first concept of service-oriented security. And the way to do it is when you create your infrastructure in EC2, you can create security groups. Now, security groups are going to be basically firewall rules, open port TCP/80 or whatnot to that source address. But security groups can also open connections to each other. You can say security group X security group Y will open the access to security group X. So they can really reference each other. And if you add 5, 10, 50 VMs in security group X, all of those VMs are going to inherit the security policy. So instead of managing IPs or hosts directly, you manage groups that are a lot easier to scale up and down because you don't have to worry about the number of instances in that group. Back to our architecture diagram. The way we can represent that architecture in very high-level security policy is just like that, except caching to front-end on TCP/80, so that just accepts all of those connections here, which means this server is going to accept everything coming from this service, and these servers here, if they have a host-based firewall, are going to be allowed to connect here. Now, you have 2 types of policies, essentially. Inter-services policies that go between one service and the other, and intra-service policies that go inside a service. And here we see, for example, that the API is allowed to connect to its database. The worker is allowed to connect to its database. But the worker here is not allowed to connect to this database here. And I'll show how we can actually manage that with Chef a little after. But this is how we describe the policy at a high level. You'll also notice there is no intermediate between the services. There is no firewall. There's nothing. The services are really the servers. The systems are talking to each other. And they have their own firewall, and they manage their own firewall. Well, they don't manage their own firewall. We tell them to use that firewall. Scalability. This is how really, one of the main problem when I started this project at Weber, one of the main problems we were trying to solve was to be able to manage those firewall rules dynamically. If we add 2 API nodes here, then we don't want to have to go in the configuration and say, hey, open the firewall for those 2 as well. But we still want point-to-point security. So the first thing that's going to happen is that those 2 new API nodes will be allowed to connect to the database, which means the database is going to detect those 2 nodes and say, I open my firewall for those 2. And then the API nodes here, when they configure themselves, they will say that they need to connect to this database, so they will open their outbound firewall as well. Then the web frontends and the API nodes will detect each other, and I'll show that Chef is really handy for that. And the web frontend will see that when there was only 1 API node before, there is no 3. So it needs to open its outbound firewall to connect to those API nodes here. And same for the API nodes, they will detect the front-end nodes and open the firewall for them. All of that is really IP table basic syntax under the hood. The magic here is how we create those IP table rules. So the tool, Chef. So if you're not highly familiar with Chef and Puppet, the way those work is Chef is a client-server architecture, and you have a Chef client binary running on the VM, the node, the server, and you have a Chef server on the other side that is accessed by the entire infrastructure. And instead of writing per script, bash scripts, or whatnot to configure a new service, a sysadmin will write a Ruby script that uses the Chef capabilities to create a new service. That means, for example, the Ruby script will contain install the package Apache, install the package PHP 5, and put that configuration file in this location with those variables. And this is what Chef does. So the sysadmin writes those recipes in a Chef language and then tells the Chef server to apply those recipes to a group of servers. So you will have a set of nodes, and you have a bare-bone VM, and you want it to be added inside the Chef infrastructure. You're going to go on that VM and say, you are now going to connect to the Chef server and request a key and be added in the pool. And you tell the Chef server, hey, I just added that new guy here, configure it. And then they talk to each other. They figure out what they need to, actually, the node is going to contact the Chef server and ask the Chef server, hey, what's my configuration? And the Chef server is going to send it everything it needs, and it will configure itself. The huge benefit of Chef is that the Chef server has a database that contains all of the nodes in the infrastructure, all of them. And you actually have all of the details of each node. You can know from the Chef server the CPU usage, the disk usage, anything. So this is really, really useful to manage an infrastructure where you have hundreds of servers and you just want to run one query to get the list of servers and know what they're running, what is the CPU usage, what is the disk usage, that kind of stuff. This is an example of search. Knife is a client for Chef, so it's just an API client, because Chef is just an API. And what Knife does, it gives you some access to Chef capabilities. And the one we're seeing here is the search capability. So Chef has its own search syntax, pretty much similar to what SQL would be, where you can search for all of the nodes that are actually running the raw web frontend and are in the environment staging. And you run that search, and the Chef server is going to give you back an answer, and that answer is going to contain all of the nodes. And here it found 3. It has frontend 1, frontend 2, and frontend 3. And what you see here is that frontend 1 is running the base role that usually contains the basic stuff that you want all the nodes to be running, and the web frontend role. So that's the basic idea. You can talk to the Chef server to manage your infrastructure. That's the idea. So I talked about that a little bit already. The way that works is that you have a server here, server 123, that will run the chef-client daemon, connect to the chef server API endpoint, authenticate itself, download a set of what they call a run list, which is just a list of scripts that this client needs to be running, and execute the scripts locally. And that's just, the execution is actually a little bit tricky to get at first because there's 2 or 3 different runs. Chef is not an easy tool to use at first. It takes really a couple of months to get used to the syntax and the logic and start writing cookbooks. So the chef client will run all of those recipes, and when it's done, it's going to tell the chef server, all right, I'm done and I succeeded, everything worked fine. If it didn't, for whatever reason, like you're trying to install Apache, but Nginx is already installed, so some files are conflicting, or the port is already used, and you cannot start the daemon, then the chef client run will fail and tell the chef server, I couldn't do it. So you can, from a management standpoint, look at the status of your infrastructure and see which ones are configuring properly and which ones are not. The other huge advantage of that your servers never get out of, they never lose their configuration, because Chef reruns every 30 minutes on each node, and if a file has changed, the Chef client is going to recreate that file, reprovision it with the values that you want to be in there. You cannot modify files locally. You need to modify them in the Chef infrastructure. So how does that help us to build firewalls? That helps us because we have a way to search for anything we want in the infrastructure. And we can use that to build policies, to say, service A needs to connect to service B. This is how we want 2 servers to communicate. Now we're going to extract the firewall rules from that. So the concept is automated generation and deletion of rules. That's important too. If a node disappears, the next time Chef reruns on another server, it's going to see that that node is not there anymore, so it's going to remove the firewall rule. One-to-one rules only. We don't open ranges. We open the IP of server A onto server B. And we don't say, hey, the /16 can connect to the database. No, we say, here's a list of 50 IPs that can connect to the database. User-specific outbound firewall, that's a capability of Netfilter that can, when you do outbound firewalling on the host, you can check which user is actually trying to create that connection. And depending on the UID, you will allow or block the connection. Generic rules, that's important. We have services that are homogeneous, and we just replicate them with different purposes. But under the hood, they're really the same thing. So instead of writing custom rules for all services, we built a set of generic rules, and we're applying them on different services. The technology, so stock Netfilter that goes directly into the Linux kernel. It's really efficient and secure. Reload at every run. Every time Chef runs, even if nothing has changed, it will reload the whole set of firewall rules. Now you're probably going to say, well, that's stupid. You're just using resources for nothing. But if you play with IP table restore, probably notice that you can restore an entire rule set in not even half a second, even if you have 20, 30, or 40,000 rules in your rule set. It's really, really efficient. The way it does that, it loads a new rule set into memory and verifies that the syntax is clear. And if it is clear, it's loaded properly, then it's going to move the pointer from the old rule set to the new one directly into the kernel. And some of the Netfilter features, fast reload, I just talked about that. The owner match, that's for the outbound firewall. Contract, that's the stateful firewall, and some stuff we're working on right now is support for NAT, support for time. When you want to block the access to your admin page at 2 a.m., you can do that in Netfilter. Support for IP set, which is useful if you have 20, 30, or not 20,000, but if you have 200 or 300 IPs, you don't want to be checking those IPs one by one. You can instead use an IP set, which is a hash that contains your IPs, and you check your rule against that hash. It's a pretty nifty feature of Netfilter. The syntax, all right. That's a basic syntax that doesn't do any search, so this is not really dynamic. but not only part of our infrastructure is in Chef right now. So we still have servers that are not in Chef, and those servers cannot be searched for. So we need to list them manually. So that syntax shows really a basic block that will run on a RabbitMQ server and allow connections on the port 5672, the RabbitMQ port, from those 3 servers. Very basic, no fanciness yet. Same thing here, except we want to open the access to the MongoDB server from Jenkins, and we want to open that access only in the staging environment, not in production. And we can do that by creating a generic rule that will technically get applied to both the staging and production servers. But with a parameter like this one, environment staging, then when Chef runs on that node, it will detect that it's not, whether it's running in production or in staging. And if it's running in production, it's going to discard the rule. Now with searches. Whoop. Nope. Yeah. Searches. This works really, really well when you have a client-server infrastructure. If you use something like OSSec, Nagios, anything, where you have a lot of clients connecting to one server, and you probably end up writing a generic rule on the server that says, all of the nodes coming from that IP range are allowed to connect to me. And in that range, you're going to have probably 30–40% of IPs that are not Nagios clients or are not OSSec clients. And you don't have a way to differentiate them except trying to do that manually, which is a huge pain in the butt. The way we can do that here with Chef is to say, this is a rule that's running on the OSSec server, and this rule will open the port 1514 to the nodes that answer the search role OSSec agent. When Chef runs on the OSSec server, it's going to execute and resolve that search. And it will obtain the list of IPs of all of the OSSec agents in the infrastructure and add those IPs into the firewall. Only those IPs, not the other nodes. And it's automatic. If a node disappears, the IP is removed. And the same way for the Outbound firewall, the OSSec server is allowed to connect to the agents. So we have the same search reversed. For role OSSec agent, the server is going to list all of the OSSec agents and open the Outbound firewall to connect to those agents. And only the OSSec user is allowed to do that. Another way of doing this is application to backend database setup. And here the sources are Node.js application, worker node, and API nodes. And that search is going to resolve to pretty much anything that's running an application and allows us to connect to the MongoDB server or whatever database that is. The notion of service tag. Okay, so say we're in a service-oriented infrastructure and we really want to open rules based on services. So the way we're going to do that is Chef has a way to tag nodes, tag VMs. And in the configuration of the node, it's going to say your tag is service X, your tag is service Y. And then in the search, you can search for the tags. You can say, my database here in service X will accept connection from any worker node or any API nodes that are in the same service. So it's going to search here for all of the nodes that share the same tag. And that same tag keyword in the Chef run is going to be expanded. And the MongoDB server, or whatever database that is here, is going to look for its own tag. It's going to look for its own tag and see, I am tagged with tag X. I want to list all of the other nodes that have the tag X as well. And I also want those nodes to be workers or API nodes. It's going to obtain a list of IPs, and only those IPs are going to be allowed to connect to itself. Same thing on service Y here. It's going to search for all the nodes that have service tag Y and only open the firewall for the same nodes. So we have a notion of service that is logical. There's no physical separation between the services. They could be running on the same hypervisors, they could be running in the same network, but their host firewall is going to constrain them to their own service. User-specific outbound rules, I mentioned that already. This is a feature of Chef, of Netfilter. I always wanted to use outbound firewalls. I've never been able to, because usually it's just impossible to list all of the outbound rules that you need to set on a server. It just doesn't work. And once you think you're done, you have a developer saying, hey, I need to connect to that server over there, but I'm blocked. So you end up trying to create the rule, and you have to do it for every single server manually. It never happens. With Chef, since everything is dynamic, you can just define the rules, generic rules, and let them populate themselves. And then the firewall will check the syntax and say, hey, you want the root user to be allowed to connect to the rsyslog server. That's great. All right. So I'm going to create a rule that says, if the owner of the socket is UID 0, root, then send it to the root chain. And then inside the root chain, you have a list of rules that are allowed for root only. Same thing with the Nagios user. Nagios user is going to be sent to the Nagios chain. Nagios chain will go say, hey, you're allowed to connect to the Nagios server, but nowhere else. So with that kind of rules, you can really lock down an environment. And you don't need to, if somebody gets on the system, chances are that hacker is going to be running as the application user. It's going to be really, really limited in where it can connect to. You're really blocking the outbound channels here. I'm not going to get into that too much. We have ways of creating rules dynamically, and then the cookbook creates their own rules. That's pretty much, once you get into Chef, you realize there's a lot of possibilities, and exploiting all of them is really interesting. Crossing environments. We typically, when we provision a service, we provision two versions of the service, one in staging, one in production. And they are isolated. The database in staging for service X cannot connect to the database in staging in service Y. But sometimes you want to open those rules. And in our security model, staging is way less secure than production. So we definitely don't want systems in staging to connect to production. But in some special cases, we want the workers in production to be able to connect to the database in staging. We will accept that in cases where developers want to be able to run tests against staging, so they need to have some sort of production data into staging. So the way we do that is there's a worker running in production here that's going to pull data from its own database and push that data, anonymize it, and push it inside the database in staging. And the firewall rule is, once again, generic for that. It tells the worker in production that it's allowed to connect in staging, and it tells the database in staging that it's allowed to receive connections from the worker in production. Some advanced feature, I'm going to skip on that. Shard name, that's once again some more fanciness to when you have a MongoDB cluster. For example, you can detect the members of a cluster by looking at their shard name. And the firewall, because it knows Chef and knows all the attributes, can list all of the nodes that share the same shard name and automatically authorize the replication link between them. Some weird rules. We left the support open for custom rules because we can't cover all of the use cases. So you can predefine rules and just put them in there, and it's going to be copied verbatim inside the rule set. I have about 4 minutes left. So some of the limitations of the system. So of course, when you use a provisioning system, you strongly depend on the security of that server. If you use Puppet, if you use CF Engine, if you use Chef, you depend on the security of those servers. And in our case, the security of the Chef server is really something we're taking care of, like really seriously. The protocol that connects Chef clients to the Chef server is already relatively secure. So it's really difficult for just anyone to talk to the Chef server. But it's a limitation of the system. And nodes can modify their own Chef attributes, so you need to be careful when opening rules based on what another node might be claiming to have. AFW works really well with homogeneous infrastructure. If you start having very different systems all over the place, then you will need to have custom rules all over the place. And it still makes your life easier, but it's just not as fancy. And some of the searches, we rely really heavily on the searches, and that puts some stress on your infrastructure. Those are some of the limitations. All right, so that's a quick overview on how we manage our firewall infrastructure. Questions? Start here.
What's the reporting capabilities as far as you're looking at, like, to ensure consistent configuration, for example, to produce for an audit or something like that? Does it have the ability to do that?
We have the ability to, at any given time, look at what firewall rules are running on what server, download those, parse them. So we know that a server is running just those rules because they are reloaded every 30 minutes. So we can say, here's the configuration we have in Chef. We are 100%, like 99.9% sure that all of the servers are running this within a window of 30 minutes. So it makes auditing a lot easier because you can search for anything from the Chef server instead of having to go to every single server. Yep.
Well, how do you manage application layer authentication along with all these rules, or are these services that you manage tend to be authenticated, like databases you tend to have to use passwords for based authentication?
We have two ways of doing that. At the firewall level, we consider that there is no authentication. So we kind of abstract everything that sits above layer 4. And we assume that whatever authentication is going to be put in place is going to be bonus. The firewall needs to be strict enough to protect the database if there's no authentication. Truth is, MongoDB has a very interesting authentication scheme, and when we started using it for some application and poking at it, we run into the problem of really not trusting its authentication scheme. So the firewall itself doesn't worry too much about the authentication. It just assumes that there's nothing else in place. It's the last resort. Then inside Chef, we have other cookbooks capabilities in Chef to allow for we configure each services differently based on what authentication they're going to support. And if a system needs to authenticate with another system, then we're going to use Chef to provision the credentials on system A to system B. Now, of course, the problem is that Chef is just a code repository. So you can't have those credentials in clear text in your code repository while they're being pushed to the destination server. So we have another cookbook that I wrote that's called Keymasters that does cryptography to protect those. And there's a key distribution server and all that stuff, but it's a whole different environment.
Are they linked together?
They're not linked together. They're not linked together. The firewall is really independent. Any other question? All right. Well, right on time. I believe it's lunchtime, so thanks a lot. And check it out from GitHub.